Now for problem 11. This one looks a little daunting, and I actually skipped over it at first because I was like, oh, I don't want to take the time to actually figure this out. But once you see how this works, it's actually pretty straightforward, and it's not even really tedious to write out, which is good because in analysis, sometimes something is, you see the answer and it's fairly easy to see, but just takes a long time to write out. Anyways, let's start with part A. Any finite subset of L1 is uniformly integrable. So let's start with fn fk k equals 1 to n be a finite subset of L1 mu. Also, let epsilon be greater than 0. For each I between 1 through n, we know that fi d mu is a finite signed measure. Now here, by fi d mu, I mean the measure of a set will be the integral over that set of fi d mu. And it's a finite sign measure because it's signed because f takes on potentially positive and negative values. And, well, that is, of course, assuming that we are in that all these functions are mapping onto the real line. We don't really know much about where these functions are mapping, or at least it's not like stated in the problem, but I think it's safe to assume for our purposes that these functions all are nice and they map into R. And so anyways, so it's a sign measure and it's finite because the function is fi is in L1. So anyways, also mu is a positive measure. And so we are going to apply theorem 3.5. So then there exists an I greater than 0 such that if the measure of the set E is less than delta, then the absolute value of the integral over E of fi d mu is less than epsilon. Then set delta equal the min of delta 1 through delta n. Then, say for all E in script m, I didn't specify that here, but I mean, of course, these are going to be measurable functions in our measured sigma algebra, which we'll just call script m as usual. So for all E in script m, if mu measure of E is less than delta, then for all I between 1 through n, let's just add in here, since mu E is less than delta I in particular, mu E fi d mu is less than epsilon. Hence, f1 through fn is uniformly integrable, because if you look above, that's literally just what the definition is. So now let's do the next part, part B. So let fn, I use parentheses for sequences. It doesn't matter what you use if you want to use curly brackets like Folland does. Anyways, let this be a sequence in L1 mu. I'll just write it like that. Suppose fn converges to f in L1, i.e. the L1 norm of the difference between fn and f converges to 0. then let epsilon be greater than 0. Since this sequence converges, it is a Cauchy sequence. So there is some natural number n which does not contain 0, such that for all n greater than or equal to capital N, the L1 norm difference between these two is less than epsilon over 2. This is because it's a Cauchy sequence in L1, so this is the type of convergence we need. So, also, what do we know? We know that the set F1 through Fn minus 1 is finite. So by part A, there exists a delta greater than 0 for all E and M if the measure of E is less than delta, then for all M from 1 to n minus 1, norm the integral of E of Fm d mu is less than epsilon over 2. So then in particular for all E and M, if measure of E is less than delta, then for all M in between 1 through capital N minus 1, the E Fm d mu is less than epsilon. Why did I write that again? This we're actually going to be using in the next step here to consider the case of M greater than or equal to N. But I just wanted to break it up and show you that things do everything that we need them to do here. So let's see here. If instead M is greater than or equal to N, then let's see here, what do we got? Integral over E of Fm d mu. This is, we do the classic analysis trick of adding something and subtracting it, and then using triangle inequality to break it up. So here we're introducing F of capital F sub capital N, and we subtract it here and we add it here, so that we have two things that we know how to control. This first one is just by bringing the absolute values inside, Fm minus Fn, one norm, and then the other side we know from the previous argument is less than epsilon over 2. So I guess this is technically a less than, whatever. And so then this is less than epsilon over 2 plus epsilon over 2, and that I believe is epsilon. So what does this mean? Hence for all epsilon greater than 0, there exists a delta greater than 0 such that for all M, the natural numbers, and for all E in script M, if the mu measure of E is less than delta, then the integral over E of Fm dm is less than or equal to epsilon. And that is exactly what we were trying to prove, because this holding for all M and N is the same thing as saying, say, for all Fm in the sequence of Fn. And so we're done.